So can we start?
Yes, sir, we can start now.
Good evening,
Yeah,
ladies
good
and
evening.
gentlemen. Hope I'm audible, right?
Yes, we can hear you, Viraj. Go ahead.
Okay. Ladies and gentlemen, a very good evening, and I warmly welcome you to the 7th workshop of the Battery Technology and Charging Infrastructure for Electric Vehicles workshop series organized by IEEE Y2N Pro. I'm Viraj Arivansha, your host for the day. To give a brief overview of this workshop series, this is a comprehensive course that offers both theoretical and practical insights into battery technologies and charging infrastructure of EVs. This series addresses the surging demand for expertise in the EV sector, focusing on battery systems and charging infrastructure. You will be able to explore the evolution, operational principles, and future advancements of EVs, delving into battery technologies and innovations aimed at enhancing efficiency and safety. Today's workshop focuses on Battery Management System 2. Before moving on, we have some important announcements to make. We have already shared these guidelines to be followed during the workshop series. However, I will read the guidelines and make sure that you follow them for a smooth session. First, a quiz would be administered at the end of the workshop series on the 5th of October, where you would be assessed on the knowledge gained. The IEEE credential certificate will be awarded only if you achieve at least 80% on the above-mentioned quiz and attend at least 80% of the sessions. Attendance will be marked at 3 given instances of the session. Therefore, please be present throughout the session. The recording of the webinar will be uploaded to the Google Classroom. Please rename yourself using the registration number provided in the handbook and your name if you haven't done so already. Today, we are honored to have a distinguished academic with us who will guide you through Battery Management System 2. Thank you, sir, for accepting our invitation and joining us today to deliver the keynote speech. Professor Xiaosong Hu, IEEE Fellow, received a PhD degree in Automotive Engineering from the Beijing Institute of Technology, Beijing, China in 2012. Between 2010 and 2012, he completed his scientific research and PhD dissertation with the Automotive Research Center, University of Michigan, Ann Arbor, MI, USA. He is currently a professor with the College of Mechanical and Vehicle Engineering, Chongqing University, Chongqing, China. His research interests include modeling and control of alternative powertrains and energy storage systems. Dr. Hu was the recipient of numerous prestigious awards and honors, including Web of Science Highly Cited Researcher by Clarivate Analytics, SAE Environmental Excellence in Transportation Award, SAO Timken Howard Simpson Automotive Transmission and Driveline Innovation Award, IEEE ITSS Young Researchers Award, and SAE Ralph Teeter Educational Award. He is also an IET Fellow and an AI Fellow. So, ladies and gentlemen, please welcome Professor Xiaosong Hu for the keynote speech on Battery Management System. Sir, the spotlight is yours.
Okay. Many thanks for your kind introduction. Okay. So I share my screen. Okay. So here we go. So can you see my slide?
Yes, sir, we can see.
Yes. Okay. So today I would like to talk about our research works on battery management algorithms. Okay. So this is my education and research background. Today's talk include the 4th session. First, why we need a battery management system. Second, battery modeling and state estimation. Third, battery thermal monitoring and management. Fourth, battery health evaluation and fault diagnosis. Okay, so as you know, energy crisis, environmental pollution, and the increasing travel demand are pushing us to develop electrified vehicles globally, right? So of course, traction battery is still the bottleneck restricting the development of electrified vehicles. The safety concern, the range anxiety, long charging time, and the high cost, all are directly related to traction battery system. Okay, traction batteries are developing towards high energy density, particularly in the car applications. But the safety problem is becoming more and more prominent. So in this sense, advanced battery control or management system is the key to break through the bottleneck of electrified transportation. Okay, in my view, there are still some key challenges for battery management system design. First, the current battery management systems typically cannot capture internal states and the parameters, so difficult to achieve optimal management. For this figure, the left figure, you can see, okay, the engine management system is relatively mature with hundreds, even thousands of metrics and estimators sensors, okay? However, for battery management system, typically we can only measure current, voltage, and a fuel cells surface temperature. So it's very challenging for us to know what inside the battery. For example, the temperature distribution inside the battery, and the usable battery power, and also the battery aging. How is the health of the battery? Okay, so we want to make the batteries more transparent, not just a black box. Okay, so there is a lot of room for us to develop advanced battery management systems. The challenge too is about the temperature applicability, particularly under extreme environments. For example, in extremely cold climate, the performance and the health of the battery will rapidly decrease. Okay. On the other hand, in super fast charging or even in very high temperature environment, thermal runaway may be happened. So we want to make our battery management systems more robust to extreme temperature conditions. Key challenge 3 is about safety concerns and the performance decay of battery systems. The capacity and the power capability of the batteries will decrease as we use the batteries, right? And also you heard some of the fire, exploding accidents for the electric vehicles. Okay, so we need to design advanced battery management systems to monitor the safety of the batteries. Okay, and we need to do the predictive maintenance if we know the remaining useful life of the batteries. Okay, so our group aims to solve these 3 key challenges and provide a basic theory and the methodology for efficient and safe operations of the battery systems. Overall, there are 3 contributions for my team. Okay, contribution 1 is about electrochemical modeling, reformulation, and multi-physics coupling, because we want to know more knowledge inside the batteries. So we need to do a lot of works on physics-based modeling. Okay. Contribution 2 is about thermal monitoring and dynamic thermal management to keep the battery safe in various temperature conditions. Contribution 3 is about intelligent battery prognostic and health management. We need to accurately estimate the battery state of health, and also we should do predict the remaining useful life for their maintenance and for resale value. Okay. So in the section 2, I will introduce our work on battery modeling and state estimation. As you know, to effectively monitor key battery internal states and parameters for better management and control, we need to build the battery model because the current sensors cannot measure parameters and states inside the battery, right? So we need to first establish the battery model to give more information about the battery. Okay, so here our work is focused on electrochemical modeling and model reformulation. Okay, this picture shows 3 types of battery models. Okay, you may know the simplest one is the equivalent circular model, right? We use some resistor or capacitor to emulate the battery dynamics, but you cannot know the physics inside the battery if you use this kind of model. So our current research focuses on the physics-based model, including P2D model and a single particle model. Okay, our future research goal is to build multi-physics model, for example, including the electrochemical and the mechanical and the aging and even your thermal model together. So, okay, this is an example we have to do how to establish the online implemented electrochemical model. Typically, the standard electrochemical model is a P2D model, but it has very high accuracy, but its complexity is very high. You cannot implement online. So we need to simplify the P2D model. Okay, so there are 2 avenues to simplify P2D model. First is we use some mathematical methods to do order reduction to reformulate this model. So we can use our computer ECU to quickly solve the equations. Okay. The second avenue is to simplify the electrode as a particle. So we call it single particle model. If we consider the electrolyte dynamics, we can develop extended single particle model with electrolyte dynamics. Okay. Basically, if we want to reformulate the electrochemical model, we need to use a spectrum method. That means we use some analytical functions, basis functions, to approximate the key quantities in the original partial differential equations. Okay, so if we use this method to simplify the whole set of PDEs, we can quickly solve the equations governing the battery dynamics. So then we use the adaptive model grid refinement technique. We can achieve rapid algorithm convergence. So from the right figure, you can see even at the 10C rate, we can get a very high accuracy, but the computational efficiency of the reformulated model is very fast. It's much faster than traditional, software like COMS or Simba. Okay, so this is some results. Okay, use this model, we can quickly mimic, for example, the lead concentration in both solid and liquid states in the batteries. Okay, also we can couple this model with thermal model. We can do some thermal emulation as well. So use this reformulated model, we can do lithium plating diagnosis, fast charging strategy optimization, and battery design optimization. Okay, so if we want integrate the thermal aspects into the electrical or equivalent circuit model, we should do electrothermal coupling. This slide shows our early work on the equivalent circuit models. Actually, we compared the 12 equivalent circuit models for both NCM and lithium iron phosphate cells. And you can see for first order RC model is the best choice for NCM batteries. But for lithium iron phosphate batteries, the first order RC model with the hysteresis model is the best choice. That shows different chemistry may need a different battery structure. Okay. And then we established, for example, the mesoscale three-dimensional electrothermal model for cylindrical batteries. That means we use the mesoscale model using finite difference method. We can establish the temperature distribution inside the batteries. Okay, but this 3D model is too complicated. We cannot, use the in real time. So we need to simplify this model. Also, we use the spectrum method. For example, polynomial or approximation. We can change the 3D to 0D, 1D, or lower order 2D models. So the simplified electrothermal models we can use in real-time system. Okay. We also established the 3D electrothermal model for pouch cell. Okay. You can see this figure. The pouch cell has different structure from the cylindrical cell. So we need to consider, for example, the internal resistance dependency on state of charge, current rate, and the temperature. And we also simplified the 3D pouch cell electrothermal model to 2D because we want to use it in our the electric vehicle ECU. Okay, we also consider the electrothermal coupling in the pack level. Okay, typically pack consists cells in series and in parallel. So we need to consider, for example, the current non-uniformity in the parallel branches. So we need to emulate this situation in the pack level. Okay, so for the state estimation, our contributions focused on model-based state of X estimation and multi-state joint estimation. Okay, actually in the past, we typically consider only one state. For example, the state of charge, right? That means the remaining energy of the battery, and the state of health, and the state of power. But in the future, and we need to consider multiple states with different time scale. Right? From the standpoint of the method, in the past, we typically use empirical-based methods like direct calculation or function mapping, even Coulomb counting to calculate the state of charge. Right? Then more and more people use model-based method. For example, we design observer camera filters to estimate the battery states. Okay, typically we use the equivalent circuit model. Some guys use physics-based models. Okay, in the future, maybe we can combine the model-based and data-driven methods to develop adaptive algorithms to implement the multi-state joint estimation. And this actually we published a review paper talking about the future trends about battery state estimation. Okay, so in my view, future battery state estimation will develop towards advanced sensing technologies like ultrasonic sensors, okay, and multi-state joint estimation, cell module, pack, scalability, safety monitoring, enhanced estimation algorithms, and the deeper applications of artificial intelligence and big data analytics. Okay, this is an example of the multi-state joint estimation. Here we actually use a model-based method. We use the simplified physics-based model, but here we didn't use camera filter observers. We use a modified moving horizon estimation. So it's a kind of online optimization method. So we use these methods to develop a hierarchical estimation framework by considering the mutual coupling between states and with different time scales. So in this framework, we can estimate the battery SOC, state of health, and the state of power. And the results is satisfactory, actually. Okay. And this slide shows we how to integrate the state of temperature into the multi-state joint estimation framework. Okay, so as shown in the left figure, we proposed an enhanced multi-state joint estimation framework for collaboratively capture the battery state of charge, state of power, and the state of temperature. Okay, we estimated the battery state of charge and state of temperature by combining adaptive filters with simplified battery models. For state of temperature estimation, we further adopted a gated recurrent unit network to enhance accuracy performance. Based on key electrothermal state estimation, we achieved the instantaneous and the continuous dynamic power capability assessments by considering multiple operational constraints. So this the proposed framework shows feasibility and high performance under various flying car cycling profiles over a wide temperature range. So the detailed performance is shown in the top right box. Okay. In the third session, we brief our works on battery thermal monitoring and management. As you know, battery thermal monitoring and management are necessary because high temperature typically cause accelerated aging and even trigger thermal runaways. On the other hand, low temperature cause power and energy decay, mainly due to the lithium plating. Okay. Third, thermal non-uniformity leads rapid performance degradation and accelerated battery aging. So we need to design advanced thermal management systems to keep the batteries work in the idle temperature range. For example, 15 Celsius degree to 35 or 40 Celsius degree, right? So here, I just emphasize our work on thermal monitoring and thermal management. In thermal monitoring, our works focused on model-based state of temperature estimation and SOC/SOT joint estimation, and sensorless surface temperature estimation. Okay, for thermal management, we developed active management strategies to ensure battery operation is in a proper temperature range. Okay, for the thermal monitoring, this slide shows our recent work on how to estimate the battery's state of charge and the three-dimensional temperature distribution simultaneously based on spatial temporal online direction. You know, for large format battery cells, there are evident thermal distributions inside the battery. So it's difficult to measure the distribution using non-invasive sensing techniques. So we need we need to design algorithms to estimate the temperature distribution. Here we use the temporal correction algorithm based on adaptive gamma filter for an accurate correction of battery SOC and the mean temperature. Then we use the corrected average temperature to restore the 3D temperature distribution. Okay, finally, the restored temperature distribution is used to adjust the parameters in the SOC estimation. So the interplay between SOC and the temperature distribution can be evidently considered in this algorithm. Okay, so this is our recent work on how to estimate the surface temperature. You may ask me why we need to estimate the surface temperature. Right? We have the temperature sensor, we can measure the surface temperature. But if you consider a battery pack with hundreds or thousands battery cells, in order to reduce the cost, we typically use a few of temperature sensors to measure just a few of cells. So we don't know the surface temperature of the remaining cells. So that's why we need to design algorithms to estimate the surface temperature of those cells based on the measured surface temperature of a few of cells is inside the battery pack. So here we proposed an accurate method to estimate the surface temperature of batteries by combining the physics-based thermal model with machine learning. As shown in the left figure, a lumped mass thermal model is applied to provide prior knowledge of battery temperatures for machine learning. Okay, the temperature-related features, such as internal resistance, can be extracted and fed into the machine learning framework to enhance accuracy. Finally, the machine learning model learns the mismatch between the model outputs and the real temperature values. Okay, as shown in the right figure, we verified our method against the various experimental results. As you can see, we can get significant accuracy improvements compared to pure thermal model-based and pure data-driven approaches. Okay, so for the thermal management, we highlight the necessity of the active dynamic thermal management. That means there is a significant temperature time lag effect. Okay, so we should consider the effect of load variation on dynamic thermal response of the battery pack. That means we need to design a predictor to predict the battery loads. For example, based on vehicle-to-vehicle, vehicle-to-infrastructure information, we can know the future battery loads in advance, right? So in this sense, we can design a model predictive thermal management strategies to adjust or optimize the thermal management system's operation in a predictive or in an anticipatory manner. Okay, so here I show an example. We in the model predictive thermal management, we can synthesize 4 control objectives, including battery temperature, temperature difference between cells, even the battery lifetime, the energy consumption of the thermal management system itself. Okay, so this is our recent work for we call it eco-cooling or eco-heating of the battery systems. Okay, in the 4th section, I will highlight our recent research work on battery health evaluation and fault diagnosis. Here, I only introduce data-driven methods because the AI method is very popular right now. So we want to use advanced AI method to do the battery aging or evaluation and do some photo diagnosis. Okay, here this slide shows the various data sets about battery aging globally. Okay, you can see there are LASA and Oxford University and some German university and Hong Kong University, and also we have our own battery aging datasets from both experiments and field data in realistic EVs. Okay, at the end of this table. Okay, if you are interested, you can download this data and to test your own battery health evaluation algorithms. Okay, with this data, we can do a lot of things. Okay, right? So our research contributions focus on health evaluation and lifetime prognostics and photo diagnosis. Okay, I will introduce more details in the next slides. Okay, here health evaluation. For data-driven battery health evaluation, you can see the whole procedure, like the right figure. Okay, first you need to have some data. Data acquisition is very important. Okay, that's why I highlight the data sets in the public. Okay, with this data, we need to do the feature engineering. That means we need to find the best or the most proper health indicators. Okay, to map the input to the battery health. Okay, with these features, we can develop various machine learning models. Okay, then we use this such machine learning model, we can do the battery health estimation. Typically, we do the capacity estimation or the power fading, right? Okay. So, in my judgment, the feature engineering is critical to the AI-based battery aging prediction or health estimation. Okay, as the left figure shows, in the past, we investigated a variety of feature extraction methods and categorized these features into two groups, measured variable and calculated variables. And then we can use a hybrid approach to select the features. This method combines the advantages of correlation analysis, filtering, and wrapper method. Okay, because we cannot measure the battery capacity or power fading in realistic operations, so we need to use some other signals to establish the battery health indicators. So this is very important. Okay, so with these features, then we consider how to develop advanced, deep learning model or AI models. Okay, in the existing works, we can see a lot of AI models for battery health assessment. Typically, they use the single model. Okay, so this motivated us to develop a multi-model framework that integrates, for example, the DNN, CNN, long short-term memory is established. So utilizing the strengths of different models, so we have the chance to improve the AI models' predictive capability. So here I should show just an example. We use the few machine learning models for the battery state of health estimation. The results you can see highlight in the red box. Our method is much better than the single model based state of health estimation methods. Okay. In order to improve the AI model's generalization, as you know, if the training data is not enough, or the training the quality of the training data is not very good, so the model's accuracy to unseen data will be decreased significantly. So we want to use some AI methods, for example, domain adaptation, to improve the generalization capability of the state of health estimation methods. Here, we use the semi-supervised, domain adapt the state of health estimation. Specifically, first, we train the base model based on, for example, a feed-forward neural network with BP, okay, using limited labeled data, okay. When faced with unlabeled data, we use the maximum mean description method for domain adaptation, as shown in the bottom right image. This method can reduce the differences in the distribution of hidden states between the target domain and the source domain. In this way, we can improve the model performance in a continuous way in facing diverse application conditions. Because in practical conditions, we typically only know a limited amount of the battery capacity values. Okay, so we need to consider the domain adaptation. So when we face with a lot of unlabeled data, okay, for the lifetime prognostics, that means we need to predict the remaining useful life of the battery, not just knowing the current health of the battery, right? So here I will show some examples of our work. Okay, here, this slide shows a very interesting work on the battery lifetime predictions. Okay, actually, existing works have some problems or the shortcomings. Okay, for example, difficulty in early prediction or no feature interpretability. Okay, here we selected the physics data hybrid features, as shown in the left figure. Here, the physics is about the difference of the anode state of deceleration, right? And the data feature is the variance of the how to say the ampere hour throughput. So we combine the data and the physics to construct the hybrid feature. Then we use the unsupervised method to do the early aging pattern clustering. So we can classify the battery cells inside the module in a pack into different types according to the aging rates. Right? For each cluster, then we can use the machine learning method to do the sequence to sequence degradation trajectory prediction. So we not just predict a point, we can predict the whole battery degradation trajectory, like the bottom right figure. Okay, so we do the sequence we call S2S battery degradation trajectory prediction. So we can give this the whole trajectory because we consider the physics. Okay, if we just only use the data-based feature, it's hard. It's hard to do the whole trajectory prediction. We can only get some points. Okay. Okay. Furthermore, we developed a semi-supervised learning for the battery degradation prediction. Why we need to do this? As I mentioned, in the real-world applications, there is a lack of labeled capacity data for model training, right? Typically, we just have a limited amount of the battery capacity values. So based on this value, this data, we first use the historic capacity curve based on our previous introduced health estimation model with a limited labeled data for transfer learning. So we first construct the whole the possible capacity curves. Then we use the capacity curves to do the AI prediction of the battery future life. So this is a kind of semi-supervised learning for the battery lifetime prediction. Okay. So in the recent months, we also developed a multitask prediction framework. That means we established the CNN, LSTM, and Bayesian neural work for multitask prediction, including battery B, end of life, lifetime state of health degradation, and age rate variations simultaneously. That means we just established one neural link, but it can fulfill multitask functions. Okay, so in the existing works, typically we need to establish multiple models for different tasks. So which may require, computational powerful computers. Okay, so here we just established one neural network to do the multitask prediction. Okay. Finally, I will introduce some works on the fault diagnosis. Okay, so here is an example. But actually, for the battery systems, there are a lot of possible faults, including the faults of the battery itself, the sensor faults, the actuator faults, right? So here, I show a model-based method to do the fault detection and isolation. Okay. Typically, we use the structural analysis theory to analyze the fault detectability, isolability, to construct the diagnostic test, like the matrix at the bottom. Okay. Then based on the matrix, we can use the, for example, extended camera filter or other observer methods to design the residual generators. We can produce a lot of generators. Then we do the residual evaluation to detect, for example, the sensor faults and other faults. Okay, so here I show some results. Actually, this matrix is very important. Okay, for this sequence, you can determine if these faults can be isolated or not. Okay. For the right figure, you can see we can observe the residual trajectory to know which faults happen. For example, if the red dashed line drift, we can find, okay, this is the sensor, the multi-sensor fault. Okay, if the green line drift, it's a temperature sensor fault. If both lamps drift, they carry the sensor. Okay, but we cannot, isolate the short circuits and the collection faults just using the residual trajectories. So in addition, so we use we calculate the entropy of the residue. We can, find, okay, for the short circuit fault, the entropy is larger than the collection fault. So we can, in this way, so we can isolate the faults of the short circuit and the collection. Okay, so this is a model-based method. Okay, so we need to firstly have the equivalent battery pack model first here. Yeah. And also we developed some data-driven algorithms to do the internal short circuit fault diagnosis. Here we use the IC curve. IC means incremental capacity curves, and local outlier factor algorithm to do the internal short circuit fault diagnosis. Okay, so actually we can use this algorithm. We can calculate the LOF value. If this value becomes larger than the normal ones, we can isolate the highly risky cells. For example, in this figure, you can see, okay, the red point is the number 49 cell is highly risky, okay? Is highly risky, okay? So here. And moreover, we also have some works on the safety warning. That means we want to, okay, give the warning signals to the drivers before, for example, the someone runaway happens or other faults happen. So how we can do that? Okay. Here we just show some results of our our collaboration project with an EV company in China. Okay. This is a real battery pack, and we have the field data about the terminal voltage, current, and a few of the battery surface temperatures. Okay, based on this data source, we use the state representation methodology, SRM. This method is a relatively complicated mathematical method. So we use this method to construct a lot of matrices, and we use the matrix calculations. We can do the state comparison. Okay, we can do the state comparisons, and we can judge if the state is normal or abnormal. So we can use this method to do the safety warning in advance. Okay, here is some results about this. Here we validated these algorithms on 4 realistic faulty vehicles. Okay, you can see the car 1, car 2, car 3, car 4, right? And the warning time in advance are different. Okay, which depends on the severity of the fault. Okay, if the severity of the fault is large, so we can, for example, here we can give the safety warning in 9 days. Okay, if the severity is very small, so the time in advance is much smaller than the 9 days. Okay, just half an hour. Okay, so okay. So I think today I just want to choose some of our research works in my team. Okay, if you guys are interested in our works on battery management algorithms, you can find more details in our papers and the patterns. Here is the website of our research team. Okay, so I hope this talk is helpful. Okay, thank you. Okay, thank you. Okay, thank you. Okay, where is the host?
Thank you very much, sir.
Yes. I think I spent 1 hour just briefing our research. Okay, Okay, due to the time limit, I cannot go to the details.
Sure. Thank you, Professor, for that informative session. Your insights have truly added depth to our participants' understanding of battery management system. I believe the foundation you have laid today will surely help our participants in the academic or professional journey. So
yeah, I think
I think
yes, go ahead. Yeah.
Sir, we are thinking of opening the floor for Q&A session. So we invite the audience to raise any questions or doubts you may have about the content that was discussed today. You may raise your hand and I will call out your name. Then you may unmute and direct your questions about the keynote speech to Professor Xiaosong Hu. Or you may use the Zoom chat to ask your questions and I will read it out to the speaker. So the Q&A session is open, so anyone can ask their doubts and clarify them if they have any.
Can I turn off my video? Actually, there is my email address, right? If you are interested in my work, our work, and if you have some questions, you can also send the email to me. Okay, I will answer your questions or your inquiries. Okay.
So I once again urge the participants to make their clarifications if there are any.
Okay, I see a message from the EV45, right?
Yeah.
Could you please explain more about the fault prognostics? Okay, I can go to the fault. I think you are interested in the fault diagnostics. Okay, here. Okay. Okay, actually, in the normal operation, okay, the battery will degrade, right? In terms of capacity and the power capability, okay. But in abnormal operations, some faults may happen. Some faults may happen. For example, I mean, you may heard some reports on battery fire explosions, right? Because of, for example, the short circuit fault. So, right, such fault belongs to the fault of the battery itself. Okay, and also for the battery system, we have some sensors, and we also have the sensor faults. Okay, and we also have the actuator for the thermal management systems. So we need to design advanced algorithms to detect those faults first, and then isolate which faults happen, and finally identify the fault level or the fault severity. Okay, so actually in our team we developed the model-based and data-driven fault diagnosis methods for the fault diagnosis. Here I just show two examples. One is model-based, the other is data-driven. For the model-based, first we use the model, right? And then measure the data, for example, the current, voltage, temperature. Then we use structural analysis. That means we derive the redundant equations to generate the residue. I show here. I show the residue right? In the right figure. Okay, the residue, and we can use the residue uh, to identify the fault, to do the fault prognostics. Okay, and also we can use the data driven. That means we just analyze the measured signals, and we compare the analyzed signal to some threshold. Okay, if the signal is larger, for example, than a threshold, we can say, okay, here is a fault. Okay. Okay, my answer is like this. Okay.
Thank you, sir. I think I hope it's clarified. If there are any more questions, please raise them.
Okay, I'm very happy to deliver this, distinguished lecture program for the audience in your country. Okay. Hope you have a chance to visit us in China. Okay, here. Yeah.
It's very much appreciated, sir.
Yeah. So, any more questions?
Yeah, I believe that's all the questions we have from the audience. Thank you, Professor, for answering and clarifying that out.
It's my pleasure. It's my pleasure. Yeah. Yeah.
Thank you very much. So moving on, we would like to take a moment to express our gratitude to our esteemed speaker. So actually, sir, if we can switch off the screen sharing, and our team would like to present you the token of appreciation. So we are greatly honored, and we would like to express our gratitude to our esteemed speaker, Professor Xiaosong Hu, for accepting our invitation and sharing his valuable knowledge and expertise with us. Please accept our token of appreciation. Your presence here has set a high standard for the caliber of learning we can expect from this workshop series. Thank you once again, sir.
Thank you. Thank you. Thank you.
Before proceeding, let's take a group photo to remember this valuable time we spent together learning today. So if we all can switch on our cameras and pose for the group photo, it would be very valuable.
Yeah.
I would like to urge you to use our virtual background as well.
Okay. Guys, you are welcome to visit us in China, huh? Yeah. I have never been to Sri Lanka. Yeah, I think I will find a chance to visit you in the future.
Yes, of course, sir.
Okay, so it's time to end the meeting.
We'll take the group photo. I think we will give a few minutes for the others to switch on their cameras as well.
Okay.
It would be very much appreciated if you could all switch on your cameras. Okay, Abra, can we get the photo, please?
Yeah. Everyone, take it.
Thank you.
Okay. Thank you very much for all. We have shared a feedback form in the Zoom chat now. Also, you can scan the QR code on the screen to access the feedback form. We kindly request you to take a few minutes to fill it out. Your feedback is extremely important to us, as it helps us to continuously improve and provide you with better experience in the future. This will also be considered for your attendance. Moving on, the next session will be on next week, 22nd of September from 6 p.m. onwards, where Dr. Sudhir Navaratna, Senior Lecturer, Department of Electrical and Electronics Engineering from University of Peradeniya, will join us to take you through predictive maintenance using IoT and big data analytics for EV. As we near the end of the session, we sincerely hope that you found the workshop informative and that you leave with new insights and ideas. And with that, we conclude today's workshop. Thank you once again and have a good night.
Okay, thank you. Thank you. Have a good night. Bye-bye. Bye-bye.
Thank you very much, sir. Good night. Bye.
Bye.